Acid-base equilibrium. How do buffers neutralize strong acids and strong bases? Specifically, what we're going to look at today is how the stress of adding a strong acid and how that affects a buffer, the stress of adding a strong base and how that affects a buffer, the effect of adding a strong acid to pure water on the pH of the resulting solution, the effect of adding a strong acid to a buffer system on pH, and finally, the effect of adding a strong acid on another buffer system on pH. Buffers with strong acids and strong bases. A buffer is made by combining 0.02 molar acetic acid and 0.02 molar sodium acetate. The total volume of the buffer solution is 500 milliliters. So in this buffer situation, we have two basic reactions going on. In reaction 1, we have acetic acid donating its acidified hydrogen to water molecules to produce the hydronium ion and also the weak base of the acetate ion. In reaction 2, we have existing acetate ions, which we know are weak bases, accepting hydrogens from water molecules to form the weak acid of acetic acid and also forming hydroxide ions. So the stress in this situation is the addition of 0.01 molar hydrochloric acid, which we know is a strong acid. Which reaction would be used to counter the stress? Since we know we're working with a strong acid, we need something to neutralize that. So if you said, hey, let's use reaction 2 because it has a hydroxide ion in it that can neutralize the hydrogen ions that are going to ionize from the hydrochloric acid, you're right. So let's see how that works. So here's my reaction where we have the weak base of the acetate ion that will accept a hydrogen from the water molecule to form the weak acid of acetic acid and also form those hydroxide ions. In comes our addition of 0.01 molar hydrochloric acid, which we know is a strong acid. So what will happen is, again, the hydrochloric acid is going to fully ionize, and when it does, we're going to have hydrogen ions. The existing hydroxide ions in solution will combine with the hydrogen ions to form water. But as a result, my concentration of hydroxide ions is going to decrease. According to Le Chatelier's principle, if I'm at equilibrium and I reduce the amount of hydroxide ions at equilibrium, I'm going to shift to replace. So this is going to shift to replace the hydroxide ions that I've taken out. As a result, my weak acid concentration is going to increase and my weak base concentration is going to decrease until equilibrium is reestablished. What would that look like in a race table? So we have acetic acid, which is my weak acid, and we have the acetate ion, which is our weak base. This H plus 1 is going to represent the addition of the strong acid of hydrochloric acid, but we're not really going to recognize the chloride ion because we know that's negligible. Before the reaction begins, we have 0.02 molar of our weak acid, and we have 0.02 molar of our weak base. The change here is the addition of the hydrogen ions. So under H plus 1, I'm going to say add 0.01 molar H plus 1. That's the stress on the system. In order to counteract the addition of this 0.01 molar, hydroxide ions in solution will be used. Therefore, my concentration of my weak base is going to go down because that, in effect, is what is neutralizing this addition of hydrogen ions. So in this column under weak base, I'm going to say minus 0.01 molar of my H plus 1 because that is what my weak base is ultimately doing by shifting to the right and replacing the hydroxide ions that were lost. As a result, as we can see above, my concentration of my weak acid has increased. So I'm going to say plus 0.01 molar to my weak acid side, because again, we can see from this shift over to the product side of this equilibrium, my weak acid has increased. As a result, all of the hydrogen ions are consumed. I have 0.01 molar of my acetate ion remaining, and I now have 0.03 molar of my acetic acid now in solution. So these would be my new concentrations after the addition of this 0.01 molar hydrochloric acid. Let's look at another example. So the stress in this situation is the addition of 0.01 molar sodium hydroxide, which we know is a strong base. Which reaction out of our initial two reactions would be used to counter the stress? And if you look below, it's pretty obvious. Because we have an excess of hydroxide ions coming into solution, we need the situation where we have the hydronium ions in solution that are going to neutralize the incoming hydroxide ions. As a result, my amount of hydronium ions is going to decrease. And if this is my left and this is my right, my equilibrium again will shift to replace what is lost. So my hydronium ions are decreasing, but as a result, my acetate ions, which we know is a weak base, will increase. At the same time, my acetic acid over on the reactant side will decrease. That is going to go down because that acetic acid needs to donate its acidified hydrogen to the existing water molecules to form the hydronium ions that are being used to neutralize the incoming hydroxide ions. So again, my acetic acid will ultimately decrease. My acetate ions, which is my weak base, will increase until equilibrium is reestablished. What does this look like in a race table? Well, we have acetic acid, which is our weak acid, and we have the acetate ion, which is our weak base. We also have the presence of our hydroxide ions right here, which will represent our stress of the addition of the 0.01 molar sodium hydroxide coming in. Before the reaction, again, we have 0.02 molar of our weak acid and 0.02 molar of our weak base, and initially, no hydroxide ions are present. The change here is the stress being added to the system. So we are adding in 0.01 molar hydroxide ions. The substance that will ultimately neutralize these hydroxide ions will be the weak acid. So we're going to take it away from the weak acid side and add that 0.01 molar over to the weak base side, because again, as this acetic acid ionizes and forms the hydronium ions, more weak base will be formed as a result as our equilibrium shifts to the right. Ultimately, all the hydroxide ions will be consumed, and as a result, our new concentrations at equilibrium after buffering has taken place will be 0.01 molar of the acetic acid remaining here and 0.03 molar of our acetate ion total once equilibrium has been reestablished. The effect of adding a strong acid to pure water on the pH of the resulting solution. 0.01 moles of HCl is added to pure water to form 500 milliliters of hydrochloric acid solution. State the initial pH of pure water, which of course we know is 7. Calculate the pH after the addition of HCl by working through the following two steps. Determine the molarity of the HCl solution and then determine the pH of the new HCl solution. So let's start out by figuring out the molarity of the HCl solution. We know that molarity is equal to moles over liters. So initially, we have 0.01 moles of hydrogen ions over 500 milliliters, which we know we have to convert that into liters, so that's going to be 0.5 liters of solution. If we divide these two, 0.01 divided by 0.5, we get 0.02 molar H plus 1 ions. We can use that number now to determine the pH of the new HCl solution. So pH is equal to the negative log of the hydrogen ion concentration. So we'll plug in our numbers. So negative log is equal to 0.02. And if we work that out, we get a pH of 1.69. So let's keep that in mind as we move on. The effect of adding a strong acid to a buffer system on pH. Determine the initial pH of a 500 milliliter buffer solution consisting of 0.125 molar acetic acid and 0.115 molar sodium acetate. The Ka of the acetic acid is 1.8 times 10 to the negative 5. If we know that our Ka is equal to 1.8 times 10 to the negative 5, we can find pKa because we know pKa is equal to the negative log of the Ka. So I'm going to substitute that in, negative log 1.8 times 10 to the negative 5. And if we work that out, we know that it will be 4.74. We can then use the Henderson-Hasselbalch equation by saying pH is equal to pKa plus the log of the concentration of our weak base over the concentration of our weak acid. So then we can plug our numbers in and say 4.74 plus the log. The concentration of our weak base is 0.115 molar. And you might say, well, where did you get that from? Well, remember, this sodium is just a spectator. We really don't acknowledge it even exists. So C2H3O2 is the acetate ion, say -1. So that's our weak base. And then the concentration of our acid is going to be 0.125 molar. So if we work that out, 4.74 plus the log of 0.115 divided by 0.125, the pH turns out to be 4.70. So this is the initial pH prior to the addition of a strong acid. Now we're going to determine the new pH of the buffer solution after the addition of 0.02 molar hydrochloric acid. So again, we're going to have our weak acid and we're going to have our weak base. We know based on our prior information that our initial concentration of our weak acid is 0.125 molar and the initial concentration of our weak base is 0.115 molar, and we don't have any strong acid added. The stress on our system is the addition of this strong acid in the form of these hydrogen ions, which would be plus 0.02 molar. So what's going to neutralize the hydrogen ions? Well, that would be the weak base, everybody. So we're going to say subtract from the weak base side 0.02 molar. And we went over the theory at the very beginning of these notes of why it's going to be the weak base. So ultimately here we're going to have 0.095 molar remaining after we subtract the 0.02. But at the same time, as this weak base neutralizes the incoming hydrogen ions, we're going to at the same time make more of our weak acid. So we're going to add 0.02 molar to our weak acid. So ultimately we'll have 0.145 molar total of our acetic acid, and the hydrogen ions have been neutralized. So the question now is, well, what's the new pH? So we're going to say pH is equal to the pKa plus log concentration of base over the concentration of our acid, because we should always write our formulas out. So we know from the work that we did on the previous slide that our pKa is 4.74 plus the log. Now what we're going to use is our new concentration after we've neutralized the incoming hydrogen ions. So the concentration of our base is now going to be a little bit lower, 0.095 molar, and the concentration of our weak acid is going to be a little higher, 0.145 molar. 4.74 plus the log of 0.095 divided by 0.145, that turns out to be a pH of 4.55. And the thing here to notice is that after the acid is neutralized, the pH has now gone down compared to our original pH because of the addition of the acetic acid as a result of the buffering behavior. So prior to buffering, our pH was 4.70. Now our pH is 4.55. And again, that's a total result of the increased amount of the acetic acid that was formed as a result of the buffering taking place. The effect of adding a strong acid on another buffer system on pH. Determine the initial pH of a 500 milliliter buffer solution consisting of 0.155 molar C2H5NH2 and 0.145 molar C2H5NH3Cl. The Kb is 5.6 times 10 to the negative 4. Okay, so the first thing that we need to do is find a Ka. If we want to use the Henderson-Hasselbalch equation, which I do, so I know that Ka times Kb is equal to Kw. So Ka is equal to Kw over Kb, which is equal to 1 times 10 to the negative 14. And my Kb is 5.6 times 10 to the negative 4. Therefore, if I work all this out, my Ka is going to be 1.78 times 10 to the negative 11. And my pKa is going to be the negative log of my Ka. So negative log of 1.78 times 10 to the negative 11. And ultimately, when I work this out, my pKa is 10.74. So pH is equal to pKa plus the log of my concentration of my weak base over the concentration of my weak acid. And now I'm going to plug in the information that's given to me. So my pKa is 10.74 plus log the concentration of my weak base, according to the information given to me, is 0.155, and the concentration of my weak acid is 0.145. So when I work this out, this is going to be my pH of 10.77, and again, this will be prior to the addition of my hydrochloric acid. So I'm going to look at this pH again after the stress of the hydrochloric acid has been added. Determine the new pH of the buffer solution after the addition of 0.02 molar HCl. So in this case, we have C2H5NH2. That's going to be my weak base. The C2H5NH3 plus 1 is going to be my weak acid. And the H plus 1, of course, is going to be the ultimate stress of adding the hydrochloric acid. Before the reaction, I have 0.155 molar of my weak base, and I have 0.145 molar of my weak acid, and the H plus 1 has not been added yet. The change in the situation is the stress of the addition of the hydrochloric acid. In this case, we're adding 0.02 molar hydrogen ions. What's going to cancel out the hydrogen ions? Well, the weak base is going to do that. So we're going to subtract it from the weak base side, and we're going to add it to the weak acid side, because again, ultimately we know that we're going to use up some of our weak base in order to neutralize the incoming hydrogen ions, but as a result of using up some of the weak base, some of the weak acid will be formed. So that means a total of 0.165 molar weak acid will be formed, and a total of 0.135 molar of weak base will be remaining. Let's see how this affects our pH. pH is equal to the pKa plus log of the concentration of my weak base over the concentration of my weak acid. So I'm going to plug my numbers in. My original pKa, which is 10.74, plus the log of my weak base, which is now 0.135 molar, divided by the concentration of my weak acid, which is now increased to 1.65 molar. And if I work all that out, I get a new pH of 10.65. This is in comparison to my original pH before the acid was added, which was 10.77. So this pH is after the acid was added. This isn't going down because of the hydrogen ions from the hydrochloric acid. This pH has decreased and become more acidic because of the increased presence of my weak acid that is now in solution. So by looking at pH prior to the addition of a stress, whether it being a strong acid or a strong base, and how that buffer acts in reaction to that stress, can tell us a lot about the buffer that we're using and how this whole process takes place. So what did you learn? We looked at the stress of adding a strong acid. We looked at the stress of adding a strong base. We looked at the effect of adding a strong acid to pure water on the pH of the resulting solution. Then we looked at the effect of adding a strong acid to a buffer system on pH. And then finally, the effect of adding a strong acid on another buffer system on pH. Need more help? Feel free to contact me. Have a great day.